Hi everyone, welcome to Unit 2. This consists of about hour and a half lectures. In Unit 1 we introduced membranes to you. We talked about some of the fundamentals, some of the membrane materials that are going to be used, certainly some of the applications, and talked very touched on a little bit about the transport mechanisms, the difference between active and passive transport. So the first part of this unit we're going to start to talk about membrane characterization. So there's the materials for making the membranes, but then we have to figure out what we've made, right? So that's where the characterization comes in. First and foremost, we usually talk about characterizing the pore size. We talked about before, there's certainly a distribution in there. They're not all uniform, which is what would be ideal, but that's not the case. We can also talk about how much free volume there is inside these membranes. If there's just one pore and a giant membrane, you're probably not going to push too much through there because your free volume, which is the volume inside that pore, is very tiny compared to the total membrane area. But you have to be careful because if you have too much free volume, you end up with a membrane that there isn't a lot of it's not chemically connected a whole lot, so you end up with something that's not very mechanically stable. So there's usually some sort of balance between those two. And this is what we refer to as the porosity. It's kind of the ratio between free volume to the total volume of the membrane. Characterization can be very complex. It's very hard, but it's also very necessary, especially for biological applications where you want to make sure that you have what you're expecting to have. If you don't have that, something can go very wrong inside someone else, inside a patient. That's obviously a very bad thing to do. So determining some of these properties, pore size and pore distribution, we can do these using a variety of techniques, which we'll get into in the lectures, so I'm just going to touch on real quick. Scanning electron microscopy we can use to actually take pictures of 2D pictures. That's key. I'm sorry, they're 3D, but you're only getting a certain cross-section, which is key because membranes can have differing pore sizes throughout the thickness of them. So you have to be a little careful in using SEM when characterizing pore sizes because the pore size might be different in other areas. We can look at the gas or liquid diffusion rates through there, and there's certain very relatively simple equations in order to use that. We can look at molecular cutoffs. That's a relatively simple way of doing it. You take especially dextrans, which are just glucose polymers, and we have different known lengths of them, and just put them over a membrane, see what comes through, see what doesn't, and then you get a relative cutoff. And you can usually model that using usually a log mean curve is what we model that with. And we can also do, if there are larger pores, we can look at different particle rejection. Silicon particles, silica particles, which are basic glass particles. So you can make those at relatively uniform lengths. Some of the other membrane properties that have an awful lot to do with separations and stuff are, so the porosity we talked about, hydrophobicity, okay, especially for proteins. Proteins tend to have, because they operate in an aqueous environment, they're surrounded by water, but there are 20 amino acid residues, and some of them are very hydrophobic. So the hydrophobic ones tend to hide on the inside of proteins because they don't want to be exposed to the water. That's just not entropically favorable. However, if your membrane is hydrophobic, when the protein hits it, it might open up or denature. And that's very bad because those proteins are going to stick, and they're stuck. They're not going to come back off. And then we can start to lose flux, lose productivity, lose selectivity, all bad things. So, like I said before, these membranes must work, especially in biomedical. They must work exactly as designed. You can imagine, say, dialysis of kidneys. That's actually the biggest market for membranes still in biomedicine is dialysis. So if certain patients' kidneys are starting to fail, starting to not work as well, toxins can build up in the blood. That's obviously very bad, for obvious reasons. And a dialysis membrane allows transfer of those toxins out, and while retaining whatever nutrients and cells and stuff that you want, basically purifying it to just water. It's very close to producing urine in your own body. So talk about let's talk about biopharmaceutical impurity removal. Those obviously also have to form at a very high level and very reproducibly, because in the case of viruses, that's the easiest example. It only takes one virus to infect a patient. And to date, at least, there's never been a viral infection because of an injection of a biopharmaceutical drug. Biopharmaceuticals are proteins, not chemicals. So they're actually made from cell lines. These cell lines, every single cell line on Earth, I'm sorry to say, has some sort of endogenous virus associated with it. Some we know about, some we don't know about. So there's a big safety factor that goes into that. So the first lecture is going to be on chemical methods of characterizing, methods such as spectroscopic methods like Fourier transport, infrared spectroscopy can look at the functional groups on the surface. XPS, which is X-ray photoelectric spectroscopy, can look at the atomic composition. And contact angle is just a way of, you basically just drop a water on top of it and see what kind of angle it has, and that's a measure of its hydrophobicity. And in the second lecture, we'll be talking about more transport methods of characterization. So those gas-liquid transports and looking at the pore sizes. We're going to be mostly doing it in a qualitative fashion because we didn't want to make this course too quantitative on you. We didn't want to make this a math course on you. So hopefully everyone will enjoy that, and that's the unit.